Hi everybody, welcome back to the Feynman Technique. Today I've got a crazy looking integral that will be solved using Feynman integration and complex numbers. So let's get started. So the first thing we're going to do is rewrite the arctangent function. Now it can be expressed as the imaginary part of a complex logarithm. Go ahead and verify this for yourself if you'd like. It requires a little bit of knowledge with being able to manipulate complex numbers, but it can be shown that for a and b are real and a is greater than 0 and also greater than b, you can express arctangent b over a as the imaginary part of the natural log of a plus bi. All right. So we take in our example, we're going to let b is equal to cosine x because we have the arctangent. This is our a over b, our b over a right here. So of course our b would be cosine x, and our a would be square root of 2 plus cosine x. And since for the real numbers x, cosine x is exists between -1 and 1 over our interval, and square root of 2 is greater than 1. So we can use this because a is going to be equal to square root of 2 plus cosine x, which is greater than or equal to the square root of 2 minus 1, which is greater than 0. So a is greater than 0. So we've satisfied this condition right here. So we can indeed rewrite our arctangent function as the imaginary part of the natural log of square root of 2 plus cosine x plus I cosine x. All right, next we're going to simplify the complex argument there. We can rewrite this just like this. This is just going to be square root of 2, and then we factor out the cosine x, giving us a 1 plus I. Next, 1 plus I, if you convert that to exponential form, that is going to be square root of 2 times e to the I pi over 4. So what we end up with is just square root of 2 times quantity 1 plus e to the I pi over 4 cosine x. All right. So the natural log of the square root of 2 plus 1 plus I times cosine x is the natural log of the square root of 2 plus the natural log of 1 plus e to the I pi over 4 cosine x. We just use the properties of logarithms. And then you'll notice that natural log square root of 2 is real. So when we take the imaginary part of it, it will go away. So the imaginary part of this expression right here is simply the imaginary part of the natural log of 1 plus e to the I pi over 4 cosine x. All right. So now we can substitute that into the integral. We've figured out that our original the arctangent portion of our integral we've just shown can be expressed as the imaginary part of the natural log of 1 plus e to the I pi over 4 cosine x. And since the integrand is real, we can bring the imaginary part out. We know that the original integral is going to be, the original integrand has to be real, so we can just bring that imaginary part right outside. So next, we're going to define a parameterized function. We're going to create an f of t. This is the Feynman integration part. So we're going to let f of t equal to the integral from 0 to pi of the natural log of 1 plus t. You can see our t is just going to replace this e to the I pi over 4 over cosine x dx. That will make it so that I is equal to the imaginary part of our function f evaluated at e to the I pi over 4. All right. And also, you will notice, I didn't write this here, but you will notice that f evaluated at 0 will be 0 because this will just become the natural log of 1, which is 0. So the whole thing will go to 0. So now we're going to differentiate f of t with respect to t using the Leibniz rule for differentiation under the integral sign, which says that you can take the derivative with respect to t of this thing right here just by passing the derivative inside as a partial derivative and leaving the rest alone. So our f prime of t is going to be equal to this right here. And in a previous video, which I will link to, I showed this formula. For a greater than the absolute value of b, we have that the integral from 0 to pi of 1 over a plus b cosine x is pi over the square root of a squared minus b squared. So with a equal 1 and b equal to t, and we have to say that the absolute value of t is less than 1 here also. F prime of t becomes pi over the square root of 1 minus t squared. Okay. So, now we're going to integrate our f prime of t to get back to f of t. So this is a standard integral right here. If we integrate this, we're just going to get pi times the arc sine of t plus c. And we know that when t is 0 in our original representation of f of t, we get the integral from 0 to pi of natural log 1 over cosine x, which is 0. So f of 0 is 0, and we can use that to solve for c. So our f of t is equal to pi arctangent t. Next, we're going to evaluate I. Well, I is simply going to be remember it was the imaginary part of our f evaluated at e to the I pi over 4. Remember, all the way up here, we stated that. I is equal to the imaginary part of our function evaluated at e to the I pi over 4. Okay, so now, we'll use the complex arcsine function representation. So arcsine z, I'm not going to show this here. You can show this using Euler's formula and the quadratic formula. You can show that arcsine z is equal to negative I natural log of iz plus the square root of 1 minus z squared. Okay, so we're going to use that. So we're going to let our z equal to e to the I pi over 4. So if z is e to the I pi over 4, our iz is I e to the I pi over 4. And our 1 minus z squared right here is just 1 minus e to the I pi over 2. Z squared is, of course, e to the I pi over 2. And e to the I pi over 2 is just I. So 1 minus z squared is 1 minus I. Therefore, the square root of z squared is going to be equal to this. And all you have to do there is rewrite this in exponential form. That's going to be the magnitude times e to the argument. And then we would square root it. So we end up with square root of the square root of 2, which is 2 to the 1/4, times e to the negative I pi over 8. And now we're just going to set w equal to this stuff in here. So w is going to be equal to iz. Well, don't forget, iz is I times e to the I pi over 4, and I is e to the I pi over 2. So we can simply say that iz is e to the I pi over 3. And then, of course, plus the square root of this thing right here, which is just plus this. So we're going to let some w equal this. Okay. Next, we're going to extract the imaginary part, because that's what we need to do. So our arcsine z is equal to negative I. Don't forget, originally it was equal to this, but now we're letting w equal this. This is our new w. So I is equal to, or arctangent z is equal to negative I natural log w. So our I is pi times the imaginary part of that. All right. So next, Well, natural log W is equal to the natural log of the magnitude of W plus I times the argument of W. So negative I natural log W is equal to negative I natural log of the argument of W plus the argument of W. Taking the imaginary part of that, we just get negative natural log W. So I is equal to negative pi times the natural log of the magnitude of W, or the absolute value of W. Okay, so now we want to actually compute what that is going to be. Well, the magnitude squared of a complex number, we can just multiply it by its conjugate. So doing that, we're going to get, let's see, this term and this term become a 1. And then we're going to have this term times this term plus this term times this term, which is going to give us this. And then plus the square root of 2. Okay, so all in all, that is equal to 1 plus the square root of 2 minus 2 to the 1/4. Now, this requires that you know the value of cosine and sine of multiples of pi over 8. But that's not hard to figure out. You can use the double angle identity or half angle identity for sine and cosine if you already know the values of cosine and sine of pi over 4. But this is what we get. We get that the magnitude squared is going to be equal to 1 plus 2, the square root of 2 minus the fourth root of 2 times the square root of quantity 2 plus square root of 2. Go ahead and stop the video and verify all this if you'd like. It's good to work all these things out by hand, but this does check out. All right. And then we can rewrite 2 to the 1/4 times square root of 2 plus square root of 2 as the square root of 2 square root of 2 plus 2. So finally, plugging that all back in, we have that our magnitude squared is 1 plus square root of 2 minus the square root of 2 times square root of 2 plus 2. All right, we are almost done. In fact, we're done. Now we just plug that in. So if this is our magnitude squared, of course, the magnitude would simply be the square root of this. So we plug that in and we get that I is equal to negative pi over 2. Don't forget, we can use the properties of logarithms to bring this square root out as a 1/2. So finally, the integral, our original integral that we started with way back at the beginning, before all this work, that integral right there, which I'm not going to say, is equal to negative pi over 2 times the natural log of 1 plus the square root of 2 minus square root of 2 square root of 2 plus 2. All right, guys, I hope you enjoyed that video, and we will see you next time.